All right, so I just wanted to slowly and deliberately go over the am I getting it that has to do with the situation where I'm starting pretty much at the origin and I walk 6 meters in the x direction, end up over here, and then walk back 6 meters. But in each of these two cases, I'm going at a different velocity. So initially, the velocity is 2 meters per second, and the velocity back is 6 meters per second. So the question is going to be, what is the position vector of me after walking that 6 meters, but before I turn around? So that's just walking over here. So there's no movement up in the y direction. So our position vector r is going to be equal to, well, we know in the y direction it's going to be 0 meters. And in the x direction, well, the position vector starts at the origin and goes to where we are, and that's going to be 6 meters. So let's see which of those. So that immediately we can see that that is C. B has them switched. It's 6 meters in the y. We didn't move at all in the y. Let's look at A. A, there's a vector on one side and just a number on the right side. You can't have a vector equal to a scalar. So that is wrong. D is actually, it is a vector because our x hat means 1, 0. So we can actually multiply it out. So it's 6 meters, 1, 0. And we'd see that we actually get 6 meters, 0 meters, which is exactly what we had over here in C. The same thing if we multiply out the x as 1, 0, and then the y as, the y is going to be 0, 1, but the 0 will be multiplied by both of these, so this term goes away, and we can see that 6 meters times x hat is exactly what D was, which is correct. F looks like it's correct, except for it doesn't have any units. So that is actually going to be wrong. And then this one also doesn't have any units, so that is wrong too. All right, so what about 2? Well, it's asking what my average velocity is during the entire trip, walking and then turning around. So that's going over these 6 meters and then coming back to that same location that I started. So how do we define our average velocity vector? Well, in the basketball activity, we defined it as the change in the position, or the displacement vector, over the amount of time that went by. And so in the numerator there, that displacement vector is going to be r final minus r initial over that change in time. But r final and r initial for the full trip, going all the way to the right and all the way back, well, we start and end both here. So this is actually these are going to cancel out because they're both 0. So this vector is going to end up being 0, 0 meters per second. It's 0 in the x and 0 in the y. Okay, so we can immediately see that A must be wrong because it's not 0. Also, similarly, E is wrong because it is not 0. What about B? Well, it's 0, but again, we have a vector on the left and we have a scalar on the right, so we need to make sure that it's 0 in x and y, so that's wrong. C is actually a vector because we do have our y, which is 1, 0, and if we multiplied our 0 times that 1, 0, we would end up getting 0, 0. We also have units of meters per second in this, so that looks correct. It is the same thing here as F, so F looks correct. Over here we have D, which similarly our y is 0, 1, and if we multiplied that by our 0, we're going to get a 0, 0, and both have units, so that is correct. And then G doesn't have any units, and it's not a vector, so that is wrong. All right, so let's check out this last one. What is my average speed, which is a scalar, not a vector, during that entire trip running and walking back? So average speed is defined as the total distance, and again, this is the distance along that path traveled, right? So up here, we traveled along a path where we went this way, and then we turned around and we came back this way. So we first went 6 meters to the right, and then we went 6 meters back. So that total distance, right, and this is divided by the time. So that total distance is going to equal 12 meters, 6 meters times 6 meters. And then what is delta t in this case? Well, our original speed was 2 meters per second. So in order for us to go 6 meters, that's going to take 3 seconds. So the trip this way, the delta t this way, is going to be 3 seconds. And then when we go back, it's 6 meters per second. And so that means the trip back is going to have a delta t of 1 second. So that's going to be 4 seconds of traveling. So we get 4 seconds down here, and that gives us 3 meters per second. And so over here, we find 3 meters per second. Nothing else has a 3 except for d, but d is a vector, and it's a vector on the right, and it's a scalar on the left, so that can't be right. All right, so now let's just quickly look at the bonus. So the bonus is asking, for each of the following equations, write an equivalent equation, or equations, because vector equations are actually hidden multiple equations, involving the vector components. So for the first one here, all we have to do is note that what we can do is think of A as ax comma ay, just in terms of its components. And we can do the same thing with our other vectors, bx by plus cx cy. And then note that we can take everything that's in the x component and we can just equate that. So actually what is equal is ax is equal to 2bx plus c, and similarly ay is equal to 2by plus cy. Now the next one is a little bit different because it's actually a scalar. It's the kinetic energy on the left, and then we have the magnitude of our vector squared here. So this is going to be equal to 1/2 m, and I'm not writing k in terms of its components because k is just a scalar. It doesn't necessarily have any vector components. So then we have our magnitude of v, and the magnitude of v squared is going to be, well, the magnitude, we just use Pythagorean theorem, vx squared plus vy squared. So that's the magnitude, but then it is squared. And then for our last one, it's sort of a combination of the previous two. So the thing to note is that this vector, this f drag vector, can be written as f drag in the x direction, comma f drag in the y direction. And on the right hand side, this magnitude can be written just as we wrote it in that second example, is just the square root of vx squared plus vy squared. And then this is actually a vector. So this is vx, vy. And so what we can do is we can take everything on the right hand side, so the minus sign, the 2, the c sub d rho a, and also this magnitude here, the magnitude of the vector, and multiply that times our vx, and that's going to be the x component of the right hand side, and we can equate that to the x component of the left hand side here. So what I mean is that f drag in the x direction is actually equal to negative 1/2 cd rho a square root of vx squared plus vy squared, and then just times vx. So we only had to change the right-hand side here by looking at that x component there. And that is how we get our x component version of this equation. And then we could do same with y subscripts. Right? And so the subscripts, I mean, are this subscript and that subscript would be y's for the y component. And so if you want to understand what just happened, you could sort of just equate this to, what if we just had something like f drag is equal to, let's say, 2c, and I'm putting just a constant in there just so that it has some units, because I'm going to write 2c equals v, and the drag and the v are vectors. And so what I am going to do is I just want to sort of show you a simpler version of this. So the simpler version is just that we'll have our f drag x, f drag y, and that's equal to 2c times vx comma vy. And what we can do is just multiply our 2c into each of these and then equate the x component and the y component, which would just be 2c times that vx, right? So we would get an equation in the x direction that's f drag x is equal to c vx. And so what we did above was just something where instead of 2c, we just had this entire thing. So I hope that was helpful, and don't hesitate to contact any of us if you have any questions.